All right, so let's now work an example with diffusivity. All right, so we're going to pull from data in Chapter 6, Table 6.2, to calculate the diffusion coefficient or diffusivity of magnesium in aluminum. So magnesium is diffusing into aluminum, and the temperature is 550 degrees Celsius. So real quickly, see if you can determine the diffusivity of this combination at 550 degrees Celsius using the expression and the data that we have here in the table. Do that. It'll be on the quiz, so go over and answer that and then come back and we'll work this together. All right, so let's go ahead and take a look at this problem. So the first, this is table 6.2, and it's asking for a diffusion coefficient for magnesium and aluminum. And so if we look down here, we got magnesium and aluminum. And so we have the D naught and the QD. So we've got this term, we've got this term, and R is a constant. And the last thing we need is T, given to us here, but we do need that in Kelvin. So we have to convert. Again, you always need the absolute when we're working these Arrhenius or these thermodynamic type equations. So if we go to the next slide, we'll see that we're plugging in the D naught here, the QD from the table in the previous slide, and then also the value for R. And we're converting the 550 degrees Celsius by adding 273 to get Kelvin. And if we do that, Kelvins cancel out, joules cancel out, the moles cancel out, and what we're left with is just the units of the pre-exponential, which are meters squared per second. And we see that the diffusivity is 6.7 times 10 to the minus 13 meters squared per second. So that's how we can calculate, pretty straightforward if we know those values of D naught and QD. I do want to draw your attention back to the previous module from last class, where in that example problem, the diffusion coefficient of carbon and iron was given to us at a specific temperature. But now we know we could go back, and if we knew what temperature and we knew the diffusing species carbon into iron, we could also calculate that given the right table of data, for example, from this table. So that's just a aside that we could do that, in fact, because we have carbon and iron data, and so we can calculate that using this data along with the temperature given to us. So we just hadn't talked about diffusivity. So that's just an aside working with this example here. All right, so I do want to go over another question related to diffusivity, but also calling back to the example problem we did in the previous lecture. So lecture 17, module 5, we dealt with the carburization question, and we had a question about how long it took to get to the concentration of 0.8 weight percent. So in this question, what we want to do is we want to see if it's treated at the same temperature and the same concentration, then how long will it take to reach the same concentration, 0.8, at double the depth, so twice the depth that was in that problem. So you're going to want to go back to this question in the previous lecture. So I'll go back to it for a second so you can see. So just to refresh your memory, in this one we were considering carburization of an alloy with a uniform concentration initially of 0.25 weight percent, treated at 950 Celsius. And the surface concentration was 1.2 weight percent, and we wanted to figure out how long it took to achieve a carbon concentration of 0.8 weight percent at a position of 0.5 millimeters below the surface. And we were given the diffusion coefficient at that temperature, but we also have the ability to calculate that now that we've talked about diffusivity. So with that information and your answers to that, see if you can come back to the current question and see if you can determine how long it will take to reach the same concentration but double the depth of that question in lecture 17, module 5. So see if you can do that. Pause the video, go answer that quiz question, and then we'll come back and we'll look at those results. All right, so let's look at this second diffusivity example that we're working. And again, this was related to lecture 17, module 5 example. And so it was asking for the same temperature, same concentration. Both of those were desired, and we're wanting to know the time it took again to reach the same concentration, Cx, right? But now the depth, so the x value, is 2 times that x value before. So we'll call this 2, and we'll call this T2, just to keep this straight. All right, so x1, so this is the depth from the first question, was 0.5 millimeters. And we want to, if we have double, that means we're talking about 1 millimeter, right? T, we don't know T2, right? We're trying to figure out what T2 is, but we knew that T1 was 7.1 hours. This is the answer to that question. So if you don't know where that comes from, go back and look at that module. And so the important thing to realize here is that the left side of that expression, right, Cx minus C naught over Cs minus C naught, right, all of these are the same. This is the same, this is the same, everything's the same. So this is a constant. And so really the only thing that's changing is the time, temperature, and then we're going to look at the diffusivity, right? So we know from the previous slides that if this is a constant, that tells us that x over dt, x squared over dt, is also a constant, right? So if anything here varies, then the other variables have to compensate for that, right? So x1 squared over dt1 is a constant, so that's going to also equal x, since the concentrations are the same, going to equal x2 squared over dt2, right? Because this is a constant, all of this is the same. In the problem statement, we showed that all of those are the same. So the only things that are changing are position and time. And in this case, diffusivity, if it's at the same temperature, right, the diffusivity is the same as well. So really what we see is that the diffusivities cancel out, and then we're left with a ratio of the depth squared over time. And we know everything but this, right? So we're going to plug in everything. So we have 0.5 millimeters squared over T1, 7.1 hours. And that's going to equal x2, which is 1.0 millimeters squared over T2. So if we solve for T2, we see that the time now increases to 28.4 hours. So by doubling the depth, the time it takes to reach that same concentration goes up from 7.1 to 28, because we're dealing with the squared term here, right? So that's the idea. So this is a simplification. So instead of trying to answer the same question all over again, right, we could easily do, or we could do that, right? We're looking for the time, we know the position, we can solve all the same concentrations, but instead of doing that all over again, we use the fact that this is a constant, meaning this expression is valid from the previous slides that you saw. And so we can set up this basically equivalency here for the combination of position 1, time 1, and position 2, time 2, and we can solve for the time. So that just allows us to simplify this problem if we know the concentrations are all the same.